Welcome all to the AI seminar at the Matrix. It is my honor to introduce Dr. Pradeep Ravikumar, who is an associate professor in the machine learning department at the School of Computer Science at CMU. His thesis at CMU has received honorable mentions in the ACM's KDD Dissertation Award and the CMU School of Computer Science Distinguished Dissertation Award. He's a Sloan Fellow, a Siebel Scholar, and recipient of the NSF Career Award. He's currently the Associate Editor-in-Chief for IEEE Transactions on Pattern Analysis and Machine Intelligence, Editor for Machine Learning Journal, and Action Editor for the Journal of Machine Learning Research. So welcome, Pradeep. We are really curious to learn more about this graceful machine learning.
Yeah.
Thank you for joining us.
Yeah, thank you for inviting me and for attending this talk. What I'm going to talk about today is what I call graceful machine learning. So to set up why we would even talk about that, the interesting thing is that if you look in the media and even in just the rough sense that people have in terms of capabilities of AI, it seems that AI can do everything, and people are in fact worried about AI taking over the world and so on. But the unfortunate reality is that even if we, let alone artificial general intelligence, even if we focus on very, very specific settings, like, I don't know, autonomous cars or healthcare or law, in many of these specific settings, we don't actually have AI that is more capable than humans, for instance. And it seems close, but somehow it's not there yet. And if you think about why that is the case, what is really lacking, the main one view for what is lacking is that most of what we do in machine learning is focused on one particular aspects of what makes a real world system work. In particular, in the machine learning academic community, we really focus on efficiency with respect to the number of samples you need to train the system, with respect to the computational resources, both in the training as well as in the runtime phase. And this is what we really focus on. And to some extent, this is reasonable in the sense that many people have argued, including philosophers, that such efficiency is highly indicative of intelligence. And so if we can achieve such high efficiency, presumably we would have achieved artificial intelligence. But the real world high stakes settings somehow seem to require something more than just sample and compute efficiency. In particular, they need various things that one can all put under the rubric of being graceful enough. So for instance, with an autonomous car, you don't just want guarantees that say that on average, right, it's pretty safe. You want a guarantee that says that when you're driving on the highway, it's not suddenly going to brake and make a U-turn and start going into the traffic in the opposite direction, right? That's the kind of thing that even novice drivers won't do. But we don't actually have guarantees on AI. And in fact, there are corner cases where even highly efficient AI do weird things like that. So how can we try to ensure that AI systems are, again, graceful enough? Again, this is a very vague term, but part of the reason for that is that we really want to put under this rubric a lot of things that we still don't understand very well in terms of how to formalize. But we still have a rough sense of what you mean by that. So towards that, I'm going to focus on two specific formalizations of graceful machine learning. But certainly that's not the end all of what I, as well as others, think of when we think of graceful machine learning. So the first is in terms of making decisions. So here I want to focus not just on building a model that, for instance, given an image, predicts whether it's a cat or a dog, right? For whatever reason, people in AI really love cat images, though that's probably true of the internet as well. Here, let's just focus on the setting where we actually want to take decisions rather than just get a model. But here, let's actually think of the decision itself as model selection. So let's just say we have two models, one which achieves zero loss with 95% probability, and it achieves a very, very high loss, let's say a loss of 100, think of 100 as being extremely large, with probability 5%. Okay, so that's one model, right? So it seems perfect 95% of the time, but it's pretty bad 5% of the time. Whereas you have another model, M2, that has a loss of 5.01 with probability 1. Okay, so it's not going to be perfect, but at the same time, it's not going to be catastrophically bad. Right? So given these two models, if we ask humans which model they would prefer, most of us would say, okay, this is maybe not perfect most of the time, but at least it's not catastrophically bad, right? So most of us would say, okay, let's just go with model M2. If these are the only two choices, let's go with model M2. But machine learning approaches would actually go with model M1. When we are training machine learning models, of course, the choices there are not just between two models, it's between many, many models, but the way it actually chooses the best performing model is by looking at expected loss. So in this case, if we just compute the expected loss, here that would be 0 times 0.95 plus 100 times 0.05, that would be the expected loss. Here for M1, it's 5.0, right? Just 5. Whereas with M2, it's 5.01. So if I compare these two models with respect to the expected loss, M2 has a greater expected loss. And so the machine learning training system would just say, hey, M2 has a higher expected loss, I'm going to go with M1. But humans would say, these two expected losses are so similar, right? But at the same time, M1 is potentially, with a decent chance, lead to a very, very high loss, right? So let's not go with M1, right? So in other words, if I have an autonomous car that on average is maybe slightly less safe, but if you can guarantee, right, that it's never going to do really weird things like just go in the opposite direction of traffic after braking, most of us would say, okay, give me that autonomous car, right? Rather than something that most of the time is better than humans, but some of the times it's just going to kill all passengers, right? But right now, the unfortunate reality is that in the way we train machine learning models is really focused on expected loss. So I see there's a question. So one of the questions is, won't they depend on the situation? Yeah, absolutely. So the specific settings would essentially have different kinds of models, and in particular, we may want to do something better than just expected loss. But in terms of training machine learning models, we actually just go with expected loss. I completely agree that we should be doing something better than expected loss. So this is something that behavioral economists, as well as behavioral scientists behavioral psychology scientists have studied in terms of how humans approach decisions. And one of the questions we wanted to ask in this work is, usually when these behavioral psychologists study the way humans may take these decisions, they think of this as cognitive distortions or cognitive errors. So they think of expected loss as a rational thing, and what humans do, which is not expected loss, is the irrational thing. Okay, so I think there's another question. Yeah. As an irrational thing, but we wanted to look at it in the opposite way, which is let's just take what humans are doing as something more interesting, and let's see if we can actually make machine learning systems learn the way humans do. To set things up, this is basically the main workhorse in machine learning. So I have some laws. So here theta indexes the model parameters. Think of it as the set of all parameters of a gigantic deep neural network. So maybe 100 million parameters. And Z is essentially your data. And it's random. Let's say a data set of images. Theta are all the parameters of my model. And L is telling me how good is this model predicting this random data point. And the way we train machine learning models is I take the average performance over my training data. But the problem in looking at average performance is that tail performance could be really bad. Economists and even folks in business, they worry about this a lot. Tail risks are very different from the expected risks, right? So in such cases, what do we do, right? But I also wanted to mention one thing, which is that just focusing on expected risk could also be very unfair, right? So let's just say we look at all of the people and say that on average, I'm going to use a system that would be very fair in deciding who has to go to jail or not, right? Let's say in the context of sentencing. But then on average, have a system that performs better, but then for all people whose name starts with P, right, it's going to put them in jail 100% of the time, right? Now, on average, right, this system could perform better, but for people like me whose name starts with P, I would say this is not very good, right? So you can have systems that on average seem better, but then its worst case performance on particular subpopulations could be arbitrarily bad. And this is essentially unfair, right? And so that also tells us that if we care about fairness, then maybe just looking at average case performance when we train a model is not the right thing. But of course, if even outside the context of fairness, like training an autonomous car, we don't just care about average case performance, we really care also about the tail risks. So the interesting thing is that if you look at how humans handle or take decisions, how they handle uncertainty. So here, this might be a little bit cryptic, but on the x-axis, think of it as essentially the quantiles. So this is the 0th quantile, meaning the smallest data point. This is the 100th percentile, meaning the largest. But what is this the smallest and largest of? Think of it as essentially, it could be anything, but think of it as the probabilities of events, okay? So this is essentially low probability events. This is extremely high probability events. So it seems, and this is what Kahneman and Tversky found, humans, when they observe probabilities of certain events, they change. So you observe a certain probability, but in your mind, you upweight and downweight probabilities. And then you take decisions based off of those upweighted and downweighted probabilities. Okay, so in particular, you may have events that are extremely low probability, like winning a lottery, say, right? So most of the lotteries, right? So it's 1 in, let's say, 300 million. Okay, so that's extremely small, but we don't think of it as 1 in 300 million, right? We just upweight it to, I don't know, 1 in 10,000 or 1 in 100,000 or something of that order. So it's a huge upweighting of the probability of winning the lottery. Similarly, when you have things, events that again are extreme in the sense, again, things that are higher risk, say, you then end up, or things that are more probable, you upweight the probability even more, okay? And then things that are kind of normal in the middle, you actually downweight their probability. So essentially, humans upweight things at the tails, at the extremes, and then they downweight things in the middle, okay? And again, if you talk to cognitive psychologists, they say that this is all a cognitive distortion. This is all the wrong thing to do. It's very unfortunate that humans don't have this black curve, right? That doesn't change the probabilities that you're observing in the real world. Now, what we said was that, why don't we actually train machine learning models with the same cognitive biases of humans? So what that means, right? So here, what am I upweighting and downweighting? So here I'm observing losses, right? So for any model, theta, again, think of this as just some neural network. This is the loss that it suffers on a random data point z. What I'm going to do is I'm going to upweight it just like how humans do, based on essentially the tails of the risk. Okay, so if tails of the loss, so in other words, if the loss is very small or very large, I'm actually going to upweight such losses, and losses that are kind of in the middle quantiles, I'm actually going to downweight those losses. Okay, and then I'm going to train a model with respect to this human cognitive bias. Okay, so we call this human risk minimization. One thing we found was that if you do this human risk minimization, it actually has reduced sensitivity to small changes in probabilities of non-extreme events. Okay, so one of the things that people are finding these days, they call this adversarial machine learning, which is that if you make small changes to the inputs, the model takes drastically different decisions. So it's very, very sensitive to small changes. What we find is that if you do this human risk minimization, these small changes in most of the space would not really cause big changes in the model's behavior, right? But that doesn't mean that it's not sensitive at all. It is more sensitive with small changes in probabilities of extreme events. Okay, now you could think of this as a bad thing, but in high stakes settings, I would argue it's a good thing, right? So in other words, if there is a small change in the probability of getting eaten by a saber-toothed tiger, right? So let's just say it's twice as likely to be eaten by a saber-toothed tiger. Should I just, be that much more worried? Maybe it's a good thing, right? Especially if you don't want to be eaten by a saber-toothed tiger, to upweight this probability even more, right? To greater than a 2-to-1 odds. And so that's basically something that we found, and that's obviously very reasonable given what we talked about so far. Another thing that again would probably be very intuitive is that let's look at 3 distributions of risk. Okay, so all 3 have the same mean. So in other words, the expectation of the 3 risk distributions are the same. So that if I were using expected risk to select the model, I wouldn't be able to distinguish between these 3 models. But let's just say I have one model with a high positive skew, meaning that there is a large tail of large risks, okay, for this distribution. And let's say there is another risk distribution where there is a large tail along for lower risks, okay. What machine learning training systems would say is that all 3 are the same, right? Because I care about expected risk. But human risk minimization would essentially say this is a very bad model. This has essentially a large tail of positive risks. And so for such positively skewed risk distributions, it would essentially say, I don't actually want to select this model. Okay, again, think of this as an autonomous car, and these are probabilities of accidents. Okay, and so if I just think of the expected, essentially the expected or average accident rate, right? All of these guys are the same thing, but then there are some distributions, let's say one autonomous car that has a long tail of really catastrophic accidents, right? Human risk minimization would say, don't give me that model, okay? Even though the expected risk of all of these guys is the same, okay? So this again makes sense based on essentially the upweighting the tails of the risk. But this is again something that arguably we may want when we want to train high stakes model, right? Not just looking at the expected risk. The other thing we found is that it cares about subgroup performance. So here we were working on this compass data set, which is basically on predicting if people are going to re-offend. Okay, so these are people who were in prison, and then the question is whether to grant them bail. And the critical question there is that, are they going to re-offend? Okay, and so here, the top here is just expected risk minimization, the usual way of training machine learning models. And what you see there is that different subgroups, so for instance, the respect to age or race or gender, have highly varying performance in terms of the error rates of this specific model that we trained. Whereas if you do human risk minimization, what we found is that, again, we don't have the overall average performance. So the average performance is still very, very similar, but the subgroup performance is also very, very similar. Okay, so different subgroups are equal before essentially this model, which is something that people might want if you're going to use this actually in a justice system. And this was something that we found even in some other contexts. So this was, for instance, another data set that people use in the context of analyzing fairness, where this is just on classifying images. Now, in the fairness literature, there isn't just one notion of fairness. There are many, many notions of fairness. Okay, and it's a rich, burgeoning field, and new papers are coming out every day on various notions of fairness. And each notion of fairness essentially entails a new way of training a machine learning model, right? And there are even some papers that say that various notions of fairness are contradictory, in the sense that if you optimize with respect to one, you would do very bad with respect to another, and so on. What we found is that, so the right column here is just expected risk minimization. It cares only about accuracy, average case performance. It doesn't care about any of your fairness criteria, right? So what we found is that if you do human risk minimization, the accuracy is very close to that of expected risk minimization, but it actually does well on a wide range of fairness issues. Okay, it's close to either the optimal or close to being the optimal with respect to various fairness desiderata. And so this is basically something. So for instance, if you compare it to a very standard, this is by no means the only algorithm, general purpose algorithm that people use. Again, any of these fairness notions has a specialized algorithm, but here is a very general purpose algorithm, which is called reweighting, which reweights the samples so that there is no dependence between whatever protected attribute or whatever subgroup ID you may have and the output or label that you're predicting. Okay, and this essentially is beaten by this human risk minimization, and this is arguably an even easier approach. Okay. So this is basically one vignette of graceful machine learning, where what we said is that looking at average risk or expected risk is not the only thing one should be doing, because in the real world, we have a whole bunch of other desiderata like fairness, like caring about subgroup performance. So I don't just care about average performance, I care about ensuring that if I just focus on a particular portion of the entire data set or the entire population, the performance in that subgroup is not going to be extremely bad, right? And in particular, all these things are related. In particular, I don't want tail risks that are extremely high. So for instance, if with all these autonomous cars, you see these statistics that say that, you know, they were running for 800,000 miles, and the if you look at the average accident rate, it's extremely low, right? But ultimately, we don't just care about average, we care about tail risks, right? How catastrophic are those accidents in certain cases? So that's basically all these other data that people are coming up with. What we found is that you can take care of all of these desiderata by actually doing things the way humans do, which is to upweight probabilities by distorting, as cognitive scientists call it, the probabilities. And that turns out to surprisingly be the right thing to do. So this was one vignette that I wanted to talk about. The other vignette that I wanted to talk about is what I call normative machine learning. So this again gets to something that a lot of practitioners complain about with respect to machine learning. So if I want to train a machine learning model, I really need a loss or a cost function. Now, usually this is fine. Usually we have some loss function, cost function that we care about. So it makes sense then to train a model that minimizes the loss, right, with respect to the training data. Of course, we usually minimize expected loss, and you can tweak that, right, like we just talked about. But modulo that, the interesting thing here is that we have some loss function, right? And many people, many statisticians, many mathematicians who have looked at from the outside at machine learning have said that part of the success in machine learning is that there is a consensus on what success means, right? In particular, if there is a particular objective or loss function that everybody agrees upon, then we can all come up with new algorithms, new models that does better on with respect to those, right? And there are also typically some benchmark data sets on which I can train and test on. And everybody, once they agree on those, they all essentially can provide performance measures of whatever things they have come up with, and then we can see which one, who has a better number, right? So this has worked remarkably well for the field of machine learning, but what if we are not sure of what the loss function we should be using should be, right? So let me give you a few examples for more complex real-world settings, right? So we don't need to, again, worry about this when we are classifying images of cats versus dogs, right? There we just want to check, are you predicting the label correctly or incorrectly? So the loss function there is pretty obvious. But what I want to, again, convey is that in the real world, there are many more complex things than classifying cats versus dogs where the loss function is not clear. So here is one example of ethics, which actually is an old example, right? It predates any of the fields that we are studying. So the high-level question, which is a very hot topic these days, is when confronted with an ethical dilemma, how should this automated AI system take an ethical decision, not just an efficient decision, but an ethical decision? Now, the unfortunate thing here is that this notion, this question of what is ethical, whether something is ethical or not, is a very, very old question. And many reasonable people have debated such questions for millennia, right? I should say millennia rather than just centuries. And there isn't a consensus on what is ethical, what is not, okay? And so that causes trouble in collecting data in even a loss function itself. Another example is, let's say I have a chatbot, right? So that again is a big topic these days. So if I have a chatbot, right, where you can just chat with this AI agent and it'll chat back, right? So you can have a conversation with this AI agent. How should it act in a socially appropriate manner, right? So in particular, right, we would prefer this agent not act in a robotic manner, right? So that's basically something that people are not happy about, right? So I don't know if you guys remember Microsoft's Clippy, which pops up and says, hey, do you want any help? And it was universally acknowledged as a really an annoying agent, right? Because it wasn't really responsive to the user's emotional and other states, right? So it was very robotic and annoying, right? So how do we make sure that the chatbots are actually acting in a more socially appropriate manner? And this again is, there's no consensus in terms of what should be the right, there isn't even a formalization of what this means, right? But this is a big open problem that the chatbots folks are trying to answer. Another example is fashion. So this is something that, for instance, Amazon came out with this thing called Eco Show, where I don't know if they still have this, but you could just it has a camera facing you, right? So it has a complete picture of how you look like, and then you can ask, is it one particular, let's say, clothing item, is this going to be fashionable with respect to you? You can ask this, and it gives you a sense of that. Okay, and so there, if you think about this, if we want to answer this question, is this fashionable, is this not? This depends on a lot of context. It depends on a particular person. It depends on the time, right? What is fashionable now is not going to be fashionable maybe 5 years from now, and so on. But the important thing is that there is no consensus. There are different fashion schools, right? And each of them may even have contradictory answers as to what counts as fashionable, right? So this again becomes tricky, right? So in other words, given an image, right, you want to predict cat versus dog, but if there's no consensus on whether this is a cat or a dog, right, then there's no consensus on the label, let alone a loss function, right? And so that's basically where a lot of things are. Here is another example of decision making with trade-offs. So these days with the COVID, there's been a lot of discussion on, approving various vaccines in a quicker manner. If you think about this, this is a very, very high stakes decision where they have to trade off questions of efficacy with safety and various other things. And the reason this is difficult is that there is no consensus on how do you trade these various competing objectives to then take a single decision, right? The single decision is essentially going to be to approve or not approve, right? But they have to trade all of these different things off. So how do you do this? So the way it's typically done is that a team of people get together and they try to form a consensus, right? And so that's why it takes so long, right? So all the data was submitted and they had to wait a month because you needed people to pore over everything and then have multiple meetings to come to a consensus for such difficult high stakes decisions. But can we automate it, right? If all the data is there, why can't we automate it, right? And the main reason we can't automate such really high stakes settings is that there is no consensus on the loss function. So in such cases, what I would argue is that we need a more flexible characterization or a way to train a machine learning model. Even without a loss function, I want a way to train a deep neural network, right? The question is how. So the one way to do this, by no means the only way, is what we call normative machine learning, which is where you specify the behavior of the machine learning model. So in other words, what it ought to, the way it ought to behave, rather than specifically specifying a loss function. Okay? So if there is a way for you to specify how the ML model ought to behave, or even give indications of how it ought to behave, that should ideally be enough for you to train a machine learning model. Okay? So this may seem a bit vague, so I want to focus on a single case study, that of ethics. Right? Again, one of the hot topics these days. So again, there is no consensus loss function, but we want to again see if there is a way for us to specify how the ML model ought to behave, then can you actually train it to be ethical? Right? And if you think about it, that is how humans train their young ones to be ethical, right? We tell them, hey, you ought to do this, hey, you ought not to do this, and so on, right? We give them this guidance, and then they automatically learn how to be ethical, right? So this is basically what we wanted to ask. And the specific thing that we were looking at was this, what people call, philosophers call the trolley problem, but in the context of autonomous cars, okay? So we have an autonomous car and its brakes have failed. And there are only two possibilities. One where in this particular example, okay? So there are two possibilities in this example where it can either go straight and then it'll kill all the passengers in the car, or it can swerve and then kill all these pedestrians. So these are, let's just say, again, this is a very stylistic example. So these are the only two possibilities, okay? And now the question is, what should the ethical system inside the autonomous car do? Should it save the passengers or should it save the pedestrians? Okay. And this is basically just an instance of a very old problem in moral philosophy called the trolley problem, where there is a trolley that is going to kill one of two sets of people. So here it's an autonomous car. Okay. Now this might seem very, very stylized and almost like a useless problem, but it does bring to bear some of the key difficulties of building an ethical system, but it's also so salient that this did attract a lot of attention in terms of people who are worried about how should autonomous cars behave when brakes are failing, even though it doesn't seem like the most critical question facing us right now. So we actually worked with some collaborators in the MIT Media Lab who were the ones who basically built this data set, which they call the model machine data set. So many of you might have heard this, but if you have not, you can actually go to the website, model machine website, and you can actually submit your ethical opinion or multiple ethical opinions, where in each ethical opinion, you'd be provided with two alternatives like this, and then you have to decide which group gets to survive. Okay, so it's a little bit morbid, but it brings to bear essentially a very difficult ethical question. So the interesting thing is that, again, because of its salience, there were millions of people from all over the world who gave essentially close to 20 million ethical opinions. And so this was the data set we were working with. And the difficulty with this, with respect to training a machine learning model, is that different people could have different opinions on what counts as ethical, right? And in fact, what we found is that there are wide cultural differences in terms of who people think should survive, right? So for instance, with respect to the young versus old, some Asian societies might be were more willing to save people who are older as opposed to Western societies. And then, but on the other hand, Western societies would be more willing to save pets as opposed to Asian societies, and so on. So there were these, if not complete extremes, there were various differences in terms of how different groups perceived as what is ethical, and in particular, these could be opposed to each other. Right? So there is the usual assumption in machine learning is that all of the data is coming from a single distribution, and that's certainly not the case, right? The other thing is that there is no loss function, right? In particular, I can't really say once, let's say I build up a model that says, okay, this is the decision that you should be taking. There is no way for me to then say, okay, let me measure the performance of the system, right? Because I don't know what is ethical, right? So I can say, hey, here is a system, right? It's just going to pick, let's say, option B, option A. How do we evaluate the system? There's no way for you to evaluate, right? You can't even ask people because different people will give you different answers. So how do you evaluate a system? You don't have a loss function. So if you can't evaluate a trained system, how do you train the system to begin with, right? So that was really the difficulty. So just to formalize this, again, the ethical opinions consisted of essentially people presented with scenarios where each scenario essentially had two alternatives, okay? And each alternative essentially you can think of as essentially a set of features related to, for instance, whether they are passengers or pedestrians, their age, whether they were crossing legally or suddenly jutted into the road and stuff like that, and a whole bunch of other features. again, if you look at that figure, there were two alternatives, and each alternative, as far as the machine learning system is concerned, it just thought of it as a set of features. Okay, so here, this is some set of features, this is another set of features, and then one person giving the ethical opinion would say that I would prefer this set of features to this set of features. Okay, so that's basically the data where people essentially gave preferences over features. So what we did was build up a model over these sets of features, which we called permutation processes, which are actually a widely used set of models in sports. So if all of us have heard of chess scores, right? And if you think in terms of chess scores, the way they actually get the score is that they actually fit a model to pairwise preferences. So let's say I would then, let's say I play with Garry Kasparov, right? So I'm definitely going to lose. But let's just say there is a small chance, maybe Garry Kasparov this is right before lunch and he's extremely hungry or something, and he has a headache. There is a small chance that I might win, right? I would argue 0, but let's just say there is a small chance. So I can essentially think of this as fitting a model or who would win between me and Garry Kasparov. And that model is basically a parameter of that model is essentially what people call the chess score. Okay. The way it works is that my performance in this game would essentially be my score plus a little bit of noise, and the performance of Garry Kasparov would be his score plus a little bit of noise, and whichever random score is better, that person wins. Okay, so it's a very stylized way of a model, but that's basically how people get scores for chess and also things like golf and so on. And that's pretty much what we wanted to do here, right? So here, instead of a score for a particular player, here we would get a score for a particular set of features. Okay, and that's basically what we did. For each person, we typically, if you go to the Model Machine website, it essentially asks you to submit at least a minimum number of ethical opinions. And the reason for that is that it would then essentially build a model of your ethical preferences. Okay, similar to think of it as a chess score. Okay, so instead of a chess score, you would get essentially like an ethics score. But don't think of this as, you know, a way of comparing different people with respect to any performance. It's just a model for how your ethical preferences are. Then, given the ethics models for multiple individuals, we aggregate all of these models for multiple individuals to a single model. Okay, and then we use the single model to then essentially take decisions. So in particular, given two alternatives, okay, then I would just compute the expected score of the two alternatives, and then I would rank them accordingly. Okay, so imagine that these were chess scores, right? Then presented with two players, let's say me and Garry Kasparov, I would just compute the expected scores, which are essentially their chess scores, and then I would rank them according to them. Okay, and then I would say whoever has the higher score, I would say that that's, in the context of chess, they are the better chess player. Here, this would be the more ethical alternative. Okay, so I know that this was a little bit vague and abstract, but hopefully you get that high-level idea of what we were doing. So that was what we did. Now here again, I want to pause to highlight a key difficulty in this entire setup, which is that this would allow us to take decisions, but how do I validate that the decisions taken by the system are actually ethical, right? We have no way of checking that, because if I ask one set of people, they would say it's ethical. Another set of people, they would say it's not ethical. How do I know what is the correct answer, right? How do I actually measure that? So what we instead do is that we say that this ethics system satisfies a bunch of properties that any system that aggregates ethical opinions should satisfy. Okay, so just to give you a sense of some of these properties, and most of us would agree these are reasonable properties. Okay, so let's just say our ethical system said that, okay, this alternative is the most ethical among a set of alternatives. Okay, so maybe I had those two scenarios, right? One with some set of passengers and one with some set of pedestrians, and it said that, okay, you know, these set of passengers are a higher priority, right? Now, let's say this was its decision. Now imagine that I went to the data set and I changed the ethical opinions of everybody to make sure they improve their ranking of alternative X. Okay. Now, after changing this data set, you again train your model, right? The way we did so, the system should continue to pick X as the most ethical alternative, right? Because the data set has only improved the standing of alternative X. Okay. So you would prefer that our training system satisfy this monotonicity property, and what we can show is that it does. Okay. There was a question. So the methods you mentioned would make the network more resistant to adversarial attacks. Yeah, absolutely. This is definitely, I think, a very, very good point that I was going to make, but you brought it up. Absolutely. And then the comment goes on to say, it will make the adversarial attacks more susceptible to less specific changes in exchange for protection for minute changes. And also, wouldn't the attacks be able to target the tails of the distribution? And wouldn't make training the adversarial networks easier? I presume this was for the first part. Yes. The second part, the second is, I guess, more susceptible to less specific. It's not clear what that means, right? But certainly the third part is a much bigger concern, which is, can you not get adversarial methods that target the tails? We actually have a paper coming out to make that robust as well. So you can take care of that as well. So there is another question. There is another question on compass and fairness. One argument I took you to be making earlier, HRM performs better on a bunch of fairness metrics and therefore is fairer, but improving performance in a given fairness metrics does not always result in fairer treatment of individuals because it's insensitive to information about risk to public posed by particular defendants. Yeah, I mean, certainly, I didn't mean to say that this resolves all questions of fairness. Certainly, if there are extremely high stakes settings where we have particular desiderata, and those could be highly individual, right? Then we should take that into account. So rather than just rely on these upweighting of tail probabilities. But this just to say that instead of taking expected risk, you just do human risk, but you can do these other things also. But doing this human risk already gets you a big way closer to where you need to be. And again, the focus on this was not really that it was optimizing towards fairness per se, right? All we wanted to do was make it closer to essentially the cognitive processing the way humans do. And that turns out to have a bunch of positive factors.
Unmute David, if you would like to ask the second part of that question.
Yeah, I mean, I guess the worry was, so it sounds like human risk will redistribute risk in lots of different ways.
Mm-hmm.
And as a result, scores on some fairness metrics will go up. But I don't think we can include that. We can conclude from that that the result is necessarily fairer treatment in any sense, because it assumes that the expected risk minimization wasn't getting things right to begin with, which could be true in some cases. So I guess, yeah.
Right. So maybe to give you a sense of why this would be fairer is that, so let's just say there are a fixed set of groups. Let's say there are 10 groups in the population. So expected risk would really measure the average performance over these 10 groups. And what this would do is that it would essentially look, look at the worst performing groups, and it would upweight the importance of those. So if you have a model that performs really badly on one particular group, then what human risk minimization would say is that the performance is actually bad, because it would upweight the loss on the bad performing group and downweight the loss on the good performing group. This is just with respect to the evaluation. And so that's basically why it is designed to make sure that you don't have a really, really bad performing group.
So in the compass example, what would be the relevant sense in which it would improve performance for, say, black defendants? Like, just what metrics are we talking about?
So there, I think it was just the accuracy of recidivism prediction in that context. But really, whatever performance measure you have, it's really a question of, should you just compute the average over all groups, or should you try to make sure that all groups don't have a really bad performance? And these are, of course, difficult questions. How much bad are you willing to go, and so on? What we did was just plug in how humans think. So instead of trying to optimize for anything, we just plugged in from the cognitive psychology literature, which wasn't really focused on fairness. We just plugged those and then just substituted that in, and it managed to do a reasonable job. So it is much more, so there's still a lot to do in terms of trying to optimize for various things. This is much more of just a vignette, if you will. Yeah, another question is asymmetry between gain and loss, like like Kahneman and Tversky found out in the context of training a machine learning system, that shouldn't matter, right? So for specifically that, I would say that is just a straight up cognitive distortion, and it shouldn't matter. In the sense that, maximizing the gain should be the same as minimizing the loss, however you define it, though humans don't consider it to be the same. But if I'm going to train a machine learning system, it's pretty much the same. So something like that, I would say, I don't mean to say all of the cognitive apparatus of humans is perfect. It's just that in this particular case, their cognitive distortions seem to actually have a interesting consequence. But it's certainly an interesting question to see what other cognitive distortions that humans have, whether we can actually see that it's actually helpful in the way we train AI systems. So the funny thing is that if you look at the way sci-fi, even if you just look at TV and movies and whatnot, has evolved over the years, initially it started off with things that were extremely robotic, right? Extremely logical and so on, to things that became more and more human-like, right? And then you had things like Battlestar Galactica, where there was very difficult to distinguish between the two. And that's really where I think we're going, where I really think that we need to look closer even at just the behavioral psychology literature rather than just neuroscience and cognitive science literature to see how humans are behaving and incorporate that in how we train machine learning systems, because they somehow seem to be helpful in acting in complex environments. So it's, I think, not enough has been done on this.
Thanks, Pradeep. I think there is a couple more questions for you.
Sure.
In the interest of time. I think Joseph, probably you want to ask a question.
Yeah, I mean, I think you addressed the core part of my question, just about sort of other cognitive biases and how those might influence the training. Maybe a brief follow-up, though. If we're training the cars to kind of do what we want people to do, then maybe, this, like, that imbalance in gains versus losses would still be valuable, in the same way that for a person to decide this wreck is really, really bad and scale that larger, you know, being 5 minutes late is much worse than the 5 minutes early.
That's actually a good point, that there is probably one threshold where things to the left is actually far, far worse than things to the right. Yeah. And like you mentioned, in terms of time, that being early is less advantageous with respect to training a model than, you know, being extremely late by crashing the car. Yeah, that's actually a good point. Yep. So even that cognitive distortion is useful. Okay, so that's great.
Thanks, I really enjoyed the talk. Thanks.
There is, thanks, Joseph. There is one more question from Peter.
Hi, thank you. Very interesting talk. I was thinking about for the moral machine, when to source subjects to establish a norm for morality, it seems very difficult to know how to sample. Like how do you deal with self-selection, and do we really want you know, the general population's view as opposed to the view of moral philosophers who spend time thinking about these things? And have you had thoughts, you know, in this area?
Right. I think that is a very important question that we don't have the right answer for, which is who should we select to construct our body of ethical opinions? I actually would prefer to lean in on the more wider democratic angle, mainly because I guess it's like a wisdom of crowds argument, where if you have a lot of independent opinions, even if they are less than ideal, if you have a lot of them, then the overall system would actually be more better trained. So if we had to restrict ourselves to just moral philosophers, there aren't enough of those. And they, of course, may themselves have some blind spots, but even setting that aside, my main worry is that we don't have enough of those. And they may also not cover the entire gamut of the range of possible ethical scenarios. So I think having as broad a base as possible is probably a good thing. But even there, I would say the thing then to worry about is to make sure we don't have selection biases of any kind. But how to ensure that is, of course, a very tricky question.
Yes, thank you. I think we're not letting you finish your talk, but there was one more question. I think there's a lot of interest.
This is actually the last slide, so that was perfect timing.
Philip?
Yeah, so I really appreciate the thoughtfulness you put into this. One thing that I see when we're talking about crowdsourcing or democratizing ethics decisions is that ethics varies so much between groups, and it varies so much between time periods. Well, what's considered ethical today or unethical today may not have had the same judgment call 50 years ago, or may not have the same judgment call if we compare Americans versus other nationalities. So defining an ethics data set, to me, runs that problem, assuming everybody is acting in good faith, assuming that you don't have particular individuals who are trying to introduce unethical biases into your data set by organizing. You know, I'm referring to internet trolls here. How do you vet these ethical data sets to account for these temporal, cultural, between group changes, and make sure that you're not letting something that, you know, would abhor one group sneak in and really bias your training set?
Right. So if there are these, and this is something we found as well, that if there are cultural and other contexts that really affect how people view things, then I would say we can focus on just that subset of people and to build essentially the data set of ethical opinions. So again, this is basically, if you think in terms of what set of people would confer legitimacy on a system. So in other words, to have the autonomous car be allowed to ply on roads in the US, who are the set of people who can confer that legitimacy? Those are the people we should query with respect to ethical opinions. So maybe people in Malaysia cannot confer legitimacy on whether it should be allowed on US roads. So let's restrict ourselves to folks in the US. Or maybe people in California have a different view as compared to, let's say, people in Pennsylvania. Then for California specific laws, let's restrict ourselves to folks in California. So I think there we can ask political scientists and so on to give us guidance on who would be the set of people to query. So in that sense, this is an advantage where you can actually tailor the training of the model to specific populations based on where they are. And you can keep retraining the model if we think that people's opinions are changing.
Okay, I think that was the last question in the chat. You may finish it up, Pradeep.
This was actually the last slide, I believe, other than thank you.
Perfect. Thank you so much. I'm sure there are a lot more follow-up questions. People might follow on with you over email if they have further questions. But thank you so much for taking time today and sharing this with us.
Yeah, and thanks for having me. It's a pleasure. Okay, thank you.
Have a good one, everyone.
Okay, thank you.